And thank you, everybody, for joining in. And it's nice to talk to everybody who even though a few of us chatted a few minutes ago, I think people are more relaxed now. The exam is over for the year, and so that's a good feeling. So I hope what we can do is talk about some things that maybe will be useful for you as you're teaching students for the last few weeks of this year, or maybe you could use them in future years. So I put a few pictures on the front slide here, the cover of the textbook, and if you haven't seen the book, Cindy can definitely get you a copy. And then also a few figures hinting at what we're going to be talking about. Here's a college dorm room, or maybe it's a high school person's room. I think, it might be a high school person's room. It's kind of messy, referring to entropy. And here's a system and what happens to energy flow going through the system. So what I want to do today, and I know some people are still connecting and some people are on but don't have audio, and so I might just repeat myself a few times in the first few minutes for the people who are coming in late. But I briefly want to describe my background as an environmental scientist. I want to describe my involvement with APES, and I want to tell you a little bit about my teaching philosophy. I want to describe our new environmental science textbook, Environmental Science for AP, which is in the end of its first cycle. That is, some of the people online and others around the country, a fair number of teachers and students have used the book, but only for this is the first year. And then I want to take some of the fundamental course topics in AP Environmental Science and connect them to big picture decision making as it is informed by life cycle assessment. And so in doing that, we'll define a system and illustrate how defining system boundaries has a large influence on what you call the, quote, impact of an action. And it really is a matter of how big you make your system, whether you include certain parts of the impact. So that's what I'd like to do. And if you're listening and you're there and you know how to use the raise the hand button, I'd love to just see quickly how many people have taught with Friedland Relier Environmental Science for AP. So I'm raising my hand and I see some hands going up, at least 3. Okay, good. So it does look like maybe a third or half the people on this WebEx today have used the book, so that's great. And so I'll go ahead and describe certain things and understand that some people are quite familiar with it and others maybe are looking to learn. I was an undergraduate environmental studies and biology major, and then I did my graduate work in environmental science, which was really in geology and earth sciences department. And I'm now a professor of environmental science in an environmental studies program. So I really enjoy the benefit of speaking to and working with environmental scientists and environmental social scientists and environmental humanists. My involvement with AP Environmental Science began in 1995 when I was asked to chair the committee that created AP Environmental Science, and I was chair for about 3 years, and we developed the first few exam offerings, and then I stepped down from that committee and shortly thereafter became the chair of my environmental studies program here at Dartmouth. And I like to watch the growth of AP Environmental Science, and I know some of you on the webcast today have participated in this. There were 5,000 exams taken in 1998, and we hit the 100,000 exam mark last year, and it looks like there are about 106,000 exams that were taken last week. So aside from that initial involvement with AP Environmental Science, they asked me back, the College Board asked me in 2008 to 2009 to participate in a curriculum development and assessment committee, which was tasked with reevaluating AP Environmental Science and looking to see if there were any changes that could be made. And while we had a lot of things to say, to my knowledge, there's none of that that's being implemented anytime in the near future. So my understanding is AP Environmental Science is staying as it is for now. And if anybody has any new information or any different information, by all means, type in a comment or something. So environmental science in the context of the AP Environmental Science curriculum is the study of the natural sciences and the interactions of the natural sciences with human beings. And maybe the exception to that is that economics is often included in the APES curriculum, just to a small extent, and economics is not something that's typically thought of as being in the natural sciences. When I teach, I like to provide breadth and depth. So I like to show people the context of the problem or the issue, but I like to also show them how you can learn a lot about it. You can go into great depth about a particular subject. And I also try to impress upon people there's so much we don't know. There's so much that we don't understand fully. I like to use quantitative reasoning when it's needed, and with some of the life cycle assessment we'll do today, you'll see how we can do some of it qualitatively and we can do it quantitatively. I try to be as neutral as I can. I've done that, I hope, in the book, and I do that in my teaching as well. That is, I don't necessarily come right out and say, nuclear energy for generating electricity is bad, and here's the way it works. Rather, I try to talk about all the good aspects of nuclear-generated electricity as well as the troublesome aspects, and maybe don't even give away my own feelings, or maybe I do that later on. And I think it's important, and I imagine all of you do as well, to use relevant examples whenever possible, not just talking about things theoretically, but how they actually are looking in the real world. And I try to use my own backyard and my students' backyard, and I imagine that's something that you do as well. So these kinds of ideas, these things in my teaching philosophy and the definition of environmental science is well represented in our book, and I think you'll see that. Our book conveys a modern synthetic approach that includes system thinking, and with life cycle assessment and understanding the big picture, it's really important to identify your system and articulate what it is and identify where it begins and where it ends, and we'll talk about that in a few minutes. We include and integrate global change, so that's global warming, but also many broader aspects of global climatic change and sustainability. We use quantitative reasoning, that is the ability to use numbers when necessary to answer questions or understand a situation. And as we were talking, some of us were talking before this WebEx got started, it's pretty clear that that ability of using numbers and numerical literacy is essential to success on the AP exam. We use relevant examples, and our book is the only one that was built from the start for AP Environmental Science, and it has designed in it a number of, I didn't know what to call these, AP-friendly features, things that will be friendly to you if you're trying to have your students be successful on the AP exam. We have do the math boxes and checkpoints and AP-style multiple choice questions at the end of every chapter, and AP-style free response questions at the end of every chapter, including approximate point distributions that you might encounter, and also a project at the end of each chapter called Measuring Your Impact, where students have to do some data gathering and some calculations. And I'll illustrate almost all of these during the slides. I have about 25 or 30 slides here, and we have, about something like 50 minutes. We'll end at 6:30 Eastern time promptly. So our book is laid out in a series of sections: introduction, the living world, biological and human populations, earth systems and resources, and so on. And those are very similar to the environmental science course descriptions that you see in the ACORN guide, the College Board booklet that you're given that outlines the course. And we've color-coded our chapters. So chapters 3, 4, and 5 are in light green. And then if you could flip over the end of the book, I don't know if this will show up on this little camera, I doubt it will, but that part of the book is coded green. And it seems to be useful for instructors and for students to be able to access the different aspects of the book from the edge of the binding. You can see that we have a series of things. This is what's circled here at the beginning. Each chapter concludes with preparing for the AP exam. So that's where we have our multiple choice questions and our free response questions. There's also a couple of other features that appear periodically, such as science applied, and we'll take a look at that. And that's taking the science and applying it to some sort of a policy or some sort of a broader societal question. So that in a nutshell is what our book looks like. And for today, I thought I'd start with a very controversial subject that's in the news a lot right now, and we're not going to answer this. This is probably a lot more than you can do in a half an hour. But I just wanted to bring up that really this whole question about obtaining oil from tar sands. Right now we're talking about a lot of this from tar sands in Alberta and Canada, and extracting those tar sands and then sending them by pipeline down through the United States to the Gulf Coast, where they would be refined into a variety of petroleum products. And one of the statements that made is obtaining oil from tar sands is much more energy intensive than obtaining oil from oil reserves in the ground, liquid petroleum reserves in the ground. And there have been a series of editorials and op-ed pieces. Here's one that showed up in the New York Times just last week, "Game over for the climate." I think that's a pretty strong statement, and this is a scientist, James Hansen, who makes it. Global warming isn't a prediction, it is happening. That is why I was so troubled to read a recent interview with President Obama in Rolling Stone in which he said that Canada would exploit the oil in its vast tar sands reserves regardless of what we do. And so this is dealing with policy, but the statement and the underlying premise that Hansen and others is using is that extracting the energy from tar sands will require much more energy, the energy embodied to get that fossil fuel energy out than conventional oil, and it will release much more CO2 than other energy sources. And to answer this, you need to do a life cycle assessment. You need to do whole system analysis of the whole system of extracting how you get the energy out of the ground, how you transport it, and then how you use it and what happens afterwards. And as I said, this is a really complex problem that would be too hard, I think, to take apart in a half an hour or so. But what we'll do is we'll do some pieces of it. And I just bring this up as one of these long, perpetual questions that is a real challenge, but it's also maybe something that gets your students very interested. So in all of this, what I've just been saying, systems are essential, and I think you'll find that systems appear throughout our book, and systems aren't always treated as uniformly across some of the other books. What is a system? A system is a set of interacting components where a change in one part of the system affects many others. I couldn't get it out of using the word in the definition. Sorry about that. We define that right up in Chapter 1. Chapter 2 is called Environmental Systems. And we go through the monolake system with inputs and outputs, and we have a smaller do the math box that allows students to calculate the input of water and the input of salt to a hypothetical lake that's just 1,000 liters in size. And we make some statements in Chapter 2. The largest system that environmental science considers is Earth. The Earth is a system. Sometimes people say considering the Earth as an ecosystem is one of the practices in environmental science. And in systems, matter and energy are important flows to understand. So we're concerned with the flows in and the flows out of matter and energy to our planet or to individual locations on the planet. In Chapter 2, our first example of showing how there are different systems, and systems are defined by the user, by the student, or by the instructor. To a physiologist, a cod is a system. So just one fish could be the entire system to a physiologist. To a marine biologist, studying studying the interaction between a predator and prey, then this two-species interrelation is a system. An oceanographer might consider the ocean currents and physical abiotic parameters and their influence on a biotic population, fish. So that might be a system, and so an oceanographer might include all of this in a system. And to somebody who's a fisheries manager, they might be interested in multiple fish populations and human activities and the shoreline and the input of pollutants from the shoreline and the extraction of materials, and you get the idea. So these are 4 different systems, each defined by a different user, by a different kind of scientist. And that's one of the points we make very early on in Chapter 2. Oftentimes in environmental science, we define systems by drawing boxes around them and putting arrows. And so again, it's the user who defines this. So one possibility is to define a system as your vehicle. If you own a particular car, you're looking at the energy inputs, such as the chemical energy in gasoline coming in, and you might look at the useful work that the car does and waste energy in terms of heat from friction in the engine, on the tires, on the brakes, and maybe some sound energy. And so this is a simple box model that shows some inputs and some outputs. And very often that is limiting yourself and limiting your understanding, your analysis to just include this. So we might want to create a larger system that goes way back here to the left and off the screen that talks about where did the fuel come from, where did the gasoline come from, and how did we get it to be able to put it in the gas tank. And in the same sense, we can talk about outputs, such as what happens to the car when it's no longer useful and it has to get recycled or disposed of somehow. So again, the point is that we define the systems by drawing boxes around things. And sometimes one person's analysis of an environmental question can come out very differently because he or she defined the system differently. So those are the kinds of things that we need to be thinking about. Here's a free response question that shows up. It actually has to do with wheat production, but it's also showing you that, and I didn't have a question that I could easily find in the book that dealt with energy systems, but here's a wheat farm being considered as an open system, and the student in this free response question is asked to identify 2 inputs and 2 outputs of this system, talking about how much is produced per hectare, how much wheat is produced per hectare, and fertilizers get added, and it doesn't say it, but wheat gets removed, that's implied. And so the student is asked to identify 2 inputs and 2 outputs of this system. And then there's a question involving feedback loops, in this case positive feedback, and the question continues. There's a part C and a part D, and I think there's a part E. But I just wanted to show you that you could go from a topic like this and then be asked to apply it to a different system, and these are done in the free response questions at the end of each chapter. As I mentioned before, we can evaluate systems qualitatively and quantitatively. And so I just wanted to point out what that difference is and what that looks like. So for example, here in our fossil fuel non-renewable energy resource chapter, we show, if you will, a life cycle assessment of energy flow through energy resource extraction and use. But we do this very qualitatively. So in this case, there's a diagram that shows the energy resource, which is presumably a seam of coal in some bedrock, and there's extraction. This looks like it's surface mining that's removing it. And then there's transportation of the coal, and there might be processing, and then it might be brought to a combustion chamber in a coal-generating electricity station where electricity is generated, there's waste products disposed of, and the electricity is transmitted along electricity transmission lines and gets to a user. So that, for example, might be not covering all, but covering what people often call cradle to grave. I suppose the grave in this case is the disposal and transportation of the waste products, the ash, and this is the end point or the desired use. And we've tried to indicate energy losses, showing that there's pretty much energy losses everywhere along the way. And so it's really important when you're going back here and you're thinking about this system, it's really important to talk about what kind of fuel are you using and how was it obtained and what happens to the waste products. So here's a qualitative diagram. And then we also have quantitative diagrams. So this is in Chapter 2 where we're first defining systems, and we show that the overall efficiency, oftentimes people raise your hand, or if you remember how Cindy showed you how to raise your hand at the top of the dialog box, raise your hand if you do something in your class where you have your students calculate the efficiency of a conversion. In this case, it's showing coal being converted to electricity. So it looks like lots of hand raising is coming in, and so pretty much everybody or maybe a couple of people are having a bite to eat and their hands are busy, but certainly a lot of people are doing that. And so in this case, one part of the system is saying if you have coal sitting at your coal-fired electricity generation station, if you have whatever the energy content of that coal is, 65% of that energy content is converted to heat and is sent up the stack. 35% of the energy in that coal is converted to electricity and then transmitted to electrical transmission lines, where about 90% of what goes into the lines ends up at people's houses and at factories. And then, depending on your machine, in this case, our machine is an incandescent light bulb, which is very inefficient. It's only about 5% efficient. A compact fluorescent might be 22% efficient, and an LED light bulb might be 25 or 30% efficient. So you would then multiply those different efficiencies to get the overall system efficiency. So in this case, it would be 0.35 times 0.9 times 0.05, which gives you a 1.6% efficiency. And when I show that to my students, I can't help but say and make the observation, wow, that is not very much of the energy that was contained within the coal that made it to light what we wanted, the work we wanted, light. And yet that doesn't even talk about the energy that was used to get the coal from the ground somewhere off to the left of this picture and get it to the electricity generating power plant. So that's this part of the step, which isn't even in this next diagram. So those are the kinds of things I think you can do, and you can illustrate that this is a qualitative life cycle assessment. This is a more quantitative, but only a partial life cycle assessment. So those are some things that I think are worth doing and getting people to think about. Here's another qualitative discussion that we put in our Chapter 2 in the text, and I've extracted it. And I said, let's compare the efficiencies in the home of how you could boil a pot of water. Some of us have homes where we have natural gas, or maybe we use wood, or in some parts of the world, people use animal waste to generate heat. And that heat in the form of a fire transfers to a pot where somebody cooks some soup or cooks a stew or something like that. And you could ask, what's the overall efficiency of that? Getting the energy in a flame to a pot, the transfer is about 50% efficient. Whereas if you have an electric coil on an electric stove, because the coils are flat and the pot comes in contact with the coils more effectively, it's actually a 70% efficient transfer right there. So if somebody just looked at the situation of electricity in some stovetop coils to a pot of food, they might say, well, that's a more efficient system. It's 70% efficient versus with wood or natural gas is only 50%, because as you've probably experienced, the heat of the flame goes elsewhere than just the pot. But that's not looking at the whole system. You have to look at how did you combust that energy, and how did you obtain that energy to make the flame, and how did you generate the electricity. And as we know from the last example, the electricity, if it's coal combustion, might only be on the order of 35% efficient. Times the 0.9, it's even closer to 30% efficient. So those are some of the things you can do in a matter of qualitative and quantitative. One thing that I like to do is show that each one of these arrows is a conversion, either an energy conversion or a phase conversion. And I like to make the point, using the first and second laws of thermodynamics, that any time there's a conversion of energy or even a transfer of energy, you tend to get some losses. So without doing a hard assessment of each of these values, some of which are hard to obtain, you could probably say that cooking with electricity has a lower overall efficiency because it has so many more conversions. And so I always find I have an electric stovetop in my house, and where I live in Vermont, there's at least 40 or so % of our electricity comes from nuclear power. And so I always think of the irony of you just want to raise the temperature of water by some tens or 100 degrees, let's say, and you sustain a nuclear reaction making steam to convert it to electricity, to convert it back to a heat product to heat up the pot of food. And so these arrows indicating many, many different conversions probably suggests that the overall efficiency of this is not as good as the overall efficiency of that. How does that sound? Does anybody have anything? Maybe I went over that a little more quickly than I wanted to, so I'm going to pause for a second. If anybody has a question or they can think of something that I left out, you could raise your hand or raise your hand and then type in a question. I'm just scanning the participants, except for some remnant hand raises from before. I think doesn't seem like anybody has anything. That's always that tricky part about these webinars is you can't read your audience. But at any rate, hopefully you see that I've done some different ones that are quantitative and qualitative, and in each case pointing out what is the system. And here's a multiple choice question that we're asking that really questions the student about some other things as well. But it says the environmental impacts of cutting down a forest to obtain wood as fuel for heating and cooking could include, and so in a way this is a kind of system analysis that's talking about how you're obtaining the fuel and then what you're doing with that fuel when you try to harness the energy in it. You release particulate matter into the air. And in this case, really this is not identifying the incorrect part of this answer, part 3, is that it doesn't lead to a large rise in sulfur dioxide. There's little or almost no sulfur dioxide coming out of wood combustion. That would be correct if, say, we were talking about coal or oil production. But for that reason, D, Roman numeral 1 and 2, would be the best choice to choose in this question. Here's another one, and I don't know if you want to go through all of it, but everybody gets very excited about fuel cells and how efficient certain aspects of having an electric car powered by hydrogen is. And that's really true. An electric motor is about 80% efficient. So an electric automobile is not quite 80% efficient, but I think it would be safe to generalize and call it that. So how do you get the hydrogen? That's the big question. A reformer generates hydrogen at about 50% efficiency, and generally a reformer can use various kinds of renewable energies like wind or solar, but the most common one to see today is natural gas. So you're taking natural gas to generate hydrogen at about 50% efficiency. And then the efficiency of transfer from the hydrogen to electricity in a fuel cell is about 80% efficient. And then, as I mentioned before, an electric motor is 80% efficient. So you can multiply it out, 0.5 by 0.5 by 0.8, and you would get an overall efficiency of this part of your system of 32%. How about a coal-generated electricity system to power an electric car? Well, we've already pointed out, I'm sorry, I used 35% before, but it's roughly the same number. 0.36 times the 0.8 efficiency of the electric motor would give you 28.8%. So in fact, even though you have another transfer here, if in this case hydrogen and a fuel cell, ignoring the cost of course, would be 32% efficient versus coal-generated electricity to power an electric car, 28%. However, the story changes if you consider natural gas-powered electricity, because natural gas conversion to electricity is 55% efficient as opposed to 35 or 36%. And the story would change even more if you talked about something like hydro or solar or wind-generated electricity. So these are all things that you can look at and do systems analyses of and maybe get to some answers. And one thing that we haven't looked at, and this gets a little bit to the tar sand question that I raised at the beginning, and that is how do we get oil out of the ground and what kinds of energy is involved in that? And you may have heard the expression well-to-wheels equation. That is, how do you get the energy from the oil well all the way to the gas tank, all the way to the wheels of your car, and then utilize it? So here's the first part of this, and this is from a very old textbook, and it's one of these diagrams that shows how much energy gets used along the way. So if you had 100 joules of energy in the ground, this diagram, with various kinds of refining being the greatest loss, shows that about 20%, 19% of the energy, or 19 joules of 100 joules in the ground, is lost along the way, and to get to roughly 80 joules of energy in the gas tank. And this is a good 30 or 40 years old, this diagram, and it's not that different today. And part of the reason is while our refining has become more efficient, sometimes to the exploitation and transport, because we're going so much further to get that oil or gas or coal or the tar sands that you then are using a lot more energy to refine. So really today, the number that you see is 80 to 85% of the energy in the ground ends up to the energy in your gas tank. And then your car, depending on whether it's a hybrid or an internal combustion or an electric vehicle, well, it wouldn't be electric with gasoline, but you then have to talk about that conversion. So this is a long way, and we are today a long way from, I don't think too many of our students know the reference to the Beverly Hillbillies, but this television program in the 1970s had this guy in Pennsylvania hunting squirrel, and his shotgun blast caused oil to come bubbling up out of the ground. So there was a seam of oil, the surface, an oil well right at the surface, and just breaking the surface of the ground caused the oil to come up. That's certainly not what we're doing today. So crude oil is deep, deep in the ground or under the ocean, or it's in another form and we have to convert it. And so that's why all of these things, this well-to-wheels equation, is so much more complicated than it used to be. And here's a diagram that I don't think you're going to be able to see very well. So if you can read any of these lines, could you do me a favor and raise your hand? I'm just curious if anybody can see it. Oh, okay, some people can. Great. I put the reference at the bottom so that you could look at this, because this is well-to-wheels emissions in grams of CO2 equivalent per mile driven. And this is showing the conventional internal combustion car and how much it is. So this is saying it's about 350 grams of CO2 equivalent per mile traveled. And it shows some different things like hybrid electrics, which are down at 250 or 275, and natural gas vehicles and diesel vehicles. And then it shows some different kinds of plug-in hybrids. So these are hybrid vehicles that also allow you to charge the battery and not use gasoline if you make short trips. And it breaks it down to the West Virginia grid mix, which has much more coal in the grid than the California grid. And it has a whole great deal of information that I think, especially this time of the year, your students are ready for it. So if you're still doing challenging projects in your class, or maybe save it for next year, you could take a look at this. And it's really looking at some different choices. And in a sense, this is all a life cycle assessment. This is the end product, but it involves what fuel went into the vehicle. And that's the kind of thing that I think is great to look at, because when you really get down to it, I should also say that if you go to the website, you'll see this makes a lot of assumptions about, how many miles are driven and so on. But if you get down to it, the best thing is to have the most efficient vehicle, the vehicle that gets the greatest number of miles per gallon or per energy content of the fuel, or if you're concerned about global climate change and you want to reduce CO2 concentrations, grams of CO2 equivalent per mile, you want to find the one that releases the least. And you don't really, it's not going to matter so much, is it hybrid, is it hybrid electric? It's just what is the one that's the least. So you'll see that some of the ones that are the least might be plug-in hybrid electric vehicles, but there are certainly some others that can have some pretty good numbers. Like here's a vehicle, it says cellulosic ethanol, and you have to, corn ethanol, and you have to wonder where's the corn coming from. We'll look at that in a second. So those are just some ideas to think of. And one graph I want to show you from Chapter 12 in our book that really is important when looking at this diagram is where you live it very much influences what your fuel mix looks like to generate electricity. So this is the average for the United States. About 45 or 48% of our electricity nationwide comes from coal. But as I mentioned, I live in Vermont, where it's about 40% nuclear and 40% hydroelectric, maybe 45-45. And I know some of you are in Ohio and in the central part of the United States where the fraction of coal might be higher. If you live on the East Coast or maybe on the West Coast, natural gas might be higher and so on. So that's a really important thing to talk about if you're going to talk about a plug-in hybrid electric car. So that's a car that for short distances, maybe 10, or if you're talking about an all-electric car, if you're getting your electricity off the grid, it's really important to talk about, where's that electricity coming from? So here's a question we have, and remember, this is a feature that I mentioned at the beginning of this WebEx that is not simulating one of the exam questions, but is rather just giving your students practice doing calculations. And like the AP exams, we're using dollars and miles and sometimes gallons of gasoline, because those are very realistically how your students, if they're buying gasoline or their parents are buying gasoline, those are the numbers they're using. So in this case, it looks at some different aspects about using a compact sedan that has a certain purchase price and gets a certain fuel efficiency, and another person pays to get a hybrid. And I think that cost differential is nowhere near as great, but it was a few years ago. Anyway, and this is just part A and part B of a problem that goes on and asks the students to fill in a table, and you can look at the rest of it on page 341 if you want to. And as I mentioned, here's a do the math, and I'm not sure everybody can fully see it, but it allows a student, it gives a student practice in calculating an energy bill or taking an energy bill and calculating what that is in kilowatt hours and how much the energy equivalent of that is and what would the dollar cost be. So there's a variety of things that some chapters have 2 or 3 do the math boxes, and all but 1 or 2 chapters have at least 1 do the math box. So these are the kinds of things that each in a little piece get you steps of the way into doing a full life cycle assessment, and then towards the end of the book you could certainly do one on your own or use one of the examples. So here's a feature I mentioned, Science Applied. It doesn't occur after every chapter, but it occurs after every section. And one of our questions is, and this is the Science Applied that appears after the 2 energy chapters, chapters 12 and 13, should corn become a fuel? And it describes the idea that a lot of people are very excited, or they were very excited about using ethanol as a fuel to replace gasoline. And one of the problems that came from the increased use of corn as a fuel is it created a scarcity of food. It created a scarcity around the world of corn that people could eat as their own human food or human fuel. So that's an issue that can be brought up that starts to push around the edges of environmental science and gets more into environmental studies, but it also brings up these issues of how connected systems are and understanding a full life cycle assessment. But is ethanol really carbon neutral, meaning does the use of ethanol, the combustion of ethanol and obtaining the energy from it, have no impact on carbon dioxide concentrations in the atmosphere? And in order to answer that, we have some text, and I'm skipping the text, but I'm showing you one of the figures. And this is an input-output analysis. This is a life cycle assessment. And it says these are the inputs of energy that you have to expend in order to get some ethanol. So you have to expend over 8 million kilojoules of energy on the farm to grow an acre of corn. So this is the energy in terms of fossil fuel to run the tractor. It might be the energy to manufacture pesticides or fertilizers if this farm uses manufactured pesticides and fertilizers. It might be energy for irrigation. It's any number of things. And so that's an input. And then another input in order to make ethanol is to convert the corn into ethanol. So that has to do with fermentation and, well, heating it, drying it, warming it, and those sorts of things. So there's an energy input there, and you can see that's quite large. And these numbers are going down as the efficiency of the operation improves from year to year. But nevertheless, it shows you that this is the amount of energy that goes into, and almost all of this, or very likely all of this, is fossil fuel energy, goes into making ethanol. What do you get out of that? Well, you get this green bar just slightly greater than the inputs in terms of the energy content of the ethanol that you produce. And some early printings of the book on page 376 actually have 3 zeros missing from this little blowout. In the text it's correct, but in this little diagram I'm afraid we left out 3 zeros, so I've corrected it here. And if you have one of the early printings of our book, you might want to correct that. Here's the break-even point, and then here's some byproducts that one would obtain, and one would have to produce them somehow, so you're getting credit for those. So this is a life cycle assessment of part of the ethanol to the corn to ethanol energy story, and you see that the payoff is something, but it's not that significant. And I have a question. What are some parts of this analysis, maybe outside of the energy realm, that are not being considered? Does anybody have one or two? There's one or two that jump out at me really significantly. Does anybody, if you raise your hand, we could unmute you, or we could just see you type it in if you want to. And everybody's shy because we haven't been talking for the last hour, and so nobody wants to say. The ones that come to me is this analysis in no way is assessing the erosion that's taking place on that farmland, because certainly almost always when you grow, unless you're under really excellent organic conditions, organic agriculture conditions, you're degrading the soil, you're reducing the organic matter content, you might be having some runoff to ponds or streams. There's also issues if there's pesticides being used, there might be depletion of an aquifer if there's irrigation. So there's all sorts of things, and so this is one of the things when you weigh it, you can say, well, yes, there's a slight energy gain, and over time we might reduce these energy inputs, and this gain might be better, but a life cycle assessment is not complete if we're only looking at the energy gains and not talking about the other consequences. And Nat Draper wrote eutrophication from the use of inorganic fertilizer. So absolutely, Nat. Eutrophication in the nearby bodies of water would be another. Almost always, even the best organic agriculture probably results in some runoff. And also I haven't mentioned habitat fragmentation. We don't know what the use of that field was beforehand, but if you're growing it as a monoculture of corn, you're not seeing the biodiversity that you might see were it left to be an old field or to become a forest again. So those are the kinds of things that you can look at with life cycle assessment. And here are some pieces. Cindy is going to either email this to you or make this PowerPoint file available to you. So here's an articulation of each of the steps, each of the bars that I showed you. And so you can look through this, and it's articulated in the book as well. So there is a surplus, a small surplus, considering that there are 33 million kilojoules or 30 million kilojoules put in. There's a small 10% surplus. And then there's another discussion that you could have with your students about in some parts of the Midwest, maybe some of you live in places near where corn is grown where you can actually get E85, gasoline product for your car that is 85% ethanol. But in most parts of the country, ethanol is a 10% additive as an oxygenator to improve the combustion of gasoline and to have less photochemical smog and nitrogen oxides formed and to have more CO2 and less carbon monoxide formed. So it's really added as an air pollution, as an additive to gasoline to improve air quality. And so the fact that it certainly isn't turning up to be, at least in the near term, as a substitute for a fossil fuel like oil. But there are chances, as you saw, there was a few words about cellulosic ethanol. So there's some possibilities that if we don't use corn to make ethanol, but we use some other products, that we might do better that way. And as I mentioned, there are some I always wonder, what are the side products when you get done distilling and making ethanol? You've got all these different things that can be used and sold, and one would have to use energy for those, so you can get some credit in the accounting for that. I have about 4 more slides, and it's 6:15. And I know we're probably, I don't know, people are getting tired. I have an example of a qualitative exam question that I wrote for my Intro to Environmental Science students at Dartmouth, most of whom are first or second year students. And it asked them about bottled water. So here's a question, and again, it shows how you can do it qualitatively and then qualitatively. So I have this thing where people send in questions to a blog, and students on their exam have to type in Twitter or write on the page of the written exam, but it's like a short answer. My environmental friends tell me that drinking bottled water is bad for the environment. I don't understand. I know that bottled water is clean, so it must be good for me, right? And I always recycle my plastic water bottles, so what's the problem? And I'm telling the student identify 2 different problems. So one way to qualitatively answer this is to say it takes energy, mostly oil, to manufacture a plastic bottle, fill it with water, and then it takes a great deal of energy to transport bottled water to stores and to consumers, especially when you compare this quantity of energy to the minimal amounts needed to obtain the same volume of water from the faucet. And this answer assumes that the water from your faucet is clean and safe to drink, and that's not true everywhere in the world, and that's not true in certain parts of this country. There's no guarantee that bottled water is any cleaner than your tap water. So I like questions like this because, one, it's a qualitative way to get someone to do a life cycle analysis. It also reaches across many parts of the ACORN guide or many parts of your course. So it's talking about energy, it's talking about life cycle and assessment, but it's also talking about water. Where does water come from? What does water quality mean? And so you can get to a lot of different things with an answer like that. A second answer might be that plastic bottles, once used, can become a solid waste problem if they're disposed of in landfills. They can become a plastic pollution problem, potentially endangering wildlife, ending up in the ocean perhaps, if not disposed of properly. And even if recycled, they require energy to transport and recycle. And furthermore, they're typically not part of a closed-loop recycling process, right? We often learn that things like plastic soda bottles and water bottles may become carpeting or polar fleece or polyester leisure suits. I don't know why, but my class always cracks up when I mention polyester leisure suits. But, it very rarely is a closed-loop recycling process. So that's the kind of thing that one could answer that question qualitatively. And then here's one. When I talk about food miles and carbon miles in my class, when I talk about energy and when I talk about food, I use some real data. I found out how many water bottles the Dartmouth Dining Service cafeterias bought last year. It was 600,000 water bottles. And I made the assumption they were 1 liter plastic bottles, and 1 liter weighs 1 kilogram when it's full of water. And I assume they were brought by truck, an average of 100 miles from a bottling plant to Dartmouth, I don't know, in Massachusetts somewhere. And I used some numbers, and I'm not going to go through it now because we're heading towards 6:20. But here is, I think, a fun kind of little exercise to get someone to appreciate how much energy in joules was needed to move water bottles to Dartmouth from Massachusetts or wherever they were, and how many liters of fuel did that take. And so I've given you the solution here. And so there was 7,200 liters, and 83 bottles is how much is transported by 1 liter of diesel fuel, just to get those bottles 100 miles. So those are some things, and I think what they point to, and again, I did right before I did take a sip of water from my little glass bottle here, and it's not necessarily that drinking water out of plastic bottles is bad, but in a qualitative way here and in a quantitative way here, you can allow your students to do the actual calculations to make the point that we don't necessarily know what the answer is, and then if you start by comparing it to something else, like what's the energy involved in turning on your tap and filling up a reusable container with water, well, one thing that the really astute student will bring up is, but wait a minute, how much energy did it take to build that water infrastructure? And that's a really great question. And how much energy did it take to put in the copper pipes and plumbing to get the faucet in your house? And so one way to do it is to say, once the water infrastructure is in, what's the trade-off in energy use to get your water one way versus the other? Or another one, it would be really hard to do, is to try to figure out, how much energy went into the water infrastructure. Those are the kinds of things you can do with life cycle assessment. And one of the philosophies in our book is not to tell people that water bottles are bad, but rather to let them look at the situation, look at the facts, and in a, I hope, relatively dispassionate way, come up. I should just point out that this was an exam question I wrote, and I don't think this exact material is in the textbook anywhere. And this is also something that I've recently written with all these discussions about food miles and carbon miles. but I bring them up as examples of things you can do with your students that allow them to participate and be doing life cycle assessment and come up with either qualitative and or quantitative responses to questions that you or they may pose. So as I mentioned at the beginning, this is the first year that our book was used in large numbers of schools around the country. And I just got this email the other day from Kathy, who said in Colorado, who said it would be okay to use her last name, but I didn't want to because she did write at the first. Last year, my class pass rate was below the national average, and I felt I had let my students down. And I just got this email yesterday or the day before, and I asked her today if it was okay to show it to all of you. I was lucky enough to be able to adopt your new text this year, and I used it with one class. I taught it cover to cover. I appreciated the parallel structure with the ACORN objectives provided by College Board. You saw I showed you that in the table of contents. Thank you for a wonderful textbooks. My kids completed every multiple choice question at the end of each chapter, and the students, after taking the exam, told her that these were helpful. My students also completed every measure your impact, and the teacher said, I appreciated the applied calculation practice in every chapter. So that's the kind of feedback we're getting, and it seems that whatever textbook you use, or if you don't use a textbook, I think it's really important to come up with qualitative and quantitative assessments of the different systems. If you can connect different systems, that's really valuable, and getting your students to do the calculations is turning out to be, in most cases, really, really valuable. And as we mentioned right before we got started, the chief reader for the APES exam, and of course this isn't the only motivation for teaching our students and letting them understand this information, but he said at the AP annual a couple of years ago, I heard him say that the best student, if they don't have the numerical literacy, is probably not going to do better than a 4 on the exam. So that is, you cannot get a 5 without having proficiency in manipulating the numbers that are going to appear in at least one, if not more, of the free response questions. So that's really the end of my prepared material. I wanted to point out that I've been having some wonderful dialogues with some of you. I certainly recognized Chris and Julie. I had met in person very early on when AP Environmental Science got started, and I recognized some other names on here, including Nat Draper, who's worked quite effectively with our teacher's resource binder, which I hope you can see here, which depending on the number of textbooks you order, you can either get this for free or you may have to pay for it. But I've had a really great dialogue with a number of you, so I'd really encourage you, andy.friedland@dartmouth.edu, send me an email. We do have, I've been not working on it enough probably, but we do have a Facebook page, Friedland and Relier Environmental Science for AP, where I post things that I think are interesting, and sometimes we get into a discussion with a bunch of the people. I mean, I think we have something like 45 likes, so it's not exactly one of the largest pages out there. But anyway, I'd encourage you to take a look if you get a chance.